And we're ready to go, David.
All right. Well, I'm going to sort of pick up where we left off last time. And one of the things I've got in here, I'm on slide 34. I don't know how many of you have a copy of the PowerPoint, but I'm going to talk about, I'm going to, huh?
Are you going to share your screen?
Yes, I am.
Okay.
Yeah, I'm just getting it cranked up as I'm talking here.
Oh, okay.
And where did the share screen go? Hold on a second.
That's on the bottom in the center.
Yeah, I know, but it went away because
okay.
I was in full screen mode. Let's see. Now, where in the world did it go? I've lost my my Zoom control screen here somewhere. Well, what in the world?
Do you want me to open it? I can open it.
No, I just, hold on, let's see. Zoom meeting. Here we go. Okay, it was off to the side there. I think it's because I had it in full screen mode. So I'm going to exit and pull it over to the side. Okay, and then start it up again. PowerPoint. And this is a lot for an old man to keep track of. Okay, there we go. Now I can share the screen. Okay, desktop 2. All right. All right, there we go. You got that? Everybody see that?
No, I can't.
Does
anybody else see it?
Nope, not me.
I don't see it either. There we go. Now I see it.
Okay.
Yeah, okay, now you're running.
All right. Now, so what I'm going to use here is an analogous situation to an experiment in a scientific decision process. So I just made up this. This is a metaphor that I teach my students, and I tell them: suppose you're out drinking and you a little high, and you're in a bar, and it's somebody that you don't know has challenged you to a game of chance, and they're going to. So if this person's going to flip a coin 100 times, and you're going to bet a dime on heads, and they're going to bet on tails each time. Now, all of us know that a fair coin, what we call a fair coin, is going to have a 50-50 chance of heads or tails. So in statistical jargon, we say then that the expected number of heads is 50. So this is a way we say it. Even though we really don't expect to get exactly 50 heads, we say that the expected value, the expected outcome is 50 heads because that is the most likely. Out of all the outcomes, that's the most likely to occur. Now, before we go into this, every single time you go into something like this, you're going to have some sort of a threshold where you consider a loss bad luck to be just bad luck, this is not my lucky day, versus something is dreadfully wrong. Do you understand what I'm talking about now? So when you're going into a game of chance, there's a certain threshold, like if you're betting on heads, there's a certain lower number of heads than 50, where you're going to say, this is not just bad luck. Something dreadfully wrong is happening here. And you're not going to accept it as bad luck. So this is a threshold region. So consider 100 flips of a fair coin. A fair coin is a 50-50 heads, tails. Okay, and so we all know that it's possible to get 100 heads straight in a row, even with a fair coin. That's possible. So everybody understands this. But it's much more likely to get a result somewhere close to 50 heads and 50 tails, somewhere close to that. But how close? How close? Where is your threshold? So the question is, if you investigate a coin for fairness with 100 flips, how far away from 50 heads would you be willing to accept as fair? So everybody understand what I'm talking about. Any questions? So, I mean, this is see, we're going to have some sort of a subconscious threshold where if we lose, so what I do is I ask my students to sort of be thinking about it. How far down in terms of number of heads would they go before they refuse to pay up to this person and say, no, I'm not paying up, because, I mean, this might be my unlucky day, but it's not that unlucky. Something is wrong with this process or with the coin or something. All right, so we've all got a threshold there. This is exactly the question scientists must ask after getting results that are consistent with prediction and sufficient, that is large enough for the effects to be useful. So this is the kind of stuff that we do when we're statistically analyzing the results of an experiment to determine the likelihood that random chance could have caused the outcome. Because if random chance could have caused the outcome, we are not justified in claiming that something other than random chance contributed to it. That's the way we make scientific decisions. And it sounds, the first time I began to realize this, I began to think, man, this is really pretty shaky grounds here. And I kept trying to figure out, there must be something wrong with the way I've got this figured out. But there's not. So I had it wrong to begin with. And I was thinking that the results of an experiment were pointing towards the conclusion, but they're actually not. And I had to, this is sort of like the turning point where I had to really come to grips with science being unable to confirm what is actually going on. So let's look at this scenario then. So 100 flips of a coin assumed fair, and we're going to bet on heads. So there's 45 heads, 40. So each of these is a loss. Now, of course, we're not going to accuse the person of cheating if we win. So this is what we call a one-directional experiment. It's sort of like with a flu vaccine, or if for instance, if they're testing a vaccine for coronavirus, they're going to want, so right now they've got a bunch of people that are injected with these vaccines, and these people are wandering around living normal lives and checking their symptoms. Now, what we're going to have is what's called a significantly lower incidence of coronavirus occurring at random in the treatment group, that is the ones that are treated with a vaccine, relative to people that are living a normal life and have not been injected. So see, that would be a one-directional test where they're expecting the results, they're predicting that the results are going to go in a particular direction. And so that's what we would be doing if we were betting on one side of a coin. And so there's 30. And so y'all be thinking about this if you're betting a dime on each of these, so that each one of these increments represents 50 cents worth of loss. And of course, it's possible to get zero by random chance. So where is your boundary?
I would say
So
that
what-
it's never happened.
Well, but see what the thing is, before you go into this, you're going to have, you've got a threshold. It may be subconscious, but like you may be thinking, like if I got down to 25 heads, I'm going to be thinking, wait a minute, this is really, really way off. And if I got down to 5 heads, I'm not going to accept that as just bad luck. I'm going to ask, let me see that coin. I'm going to flip it over and see if it's got heads on both, or see if it's got tails on both sides or something. Or I'm going to start watching him about his flipping mechanism, see if he's favoring one side or the other. So there's a threshold somewhere along this gradient here where I'm going to say, you know what, this is not just bad luck. Something is wrong here. This is not random chance. Something other than random chance is contributing to this outcome. Now, the way we do this in science, see, most people choose something around 25 or 20. Where are y'all on this? Is that right? About right? 25 or 20 is where you would accuse a person of cheating? And it's because it's sort of like halfway between even and a total loss. So most people are right in here, and they're 25 or less most of the time. Hardly anybody ever gets it right. Hardly anybody gets it right. Now, so here's what people are thinking about when they make these decisions. They're thinking about, if I accuse this person of cheating, what's going to happen? You know, if you're in a bar and people are drinking, you could get hurt. Or if you're out on the street corner in the dark and this person's got a bunch of knife scars on their face, you know, you could get hurt really bad. So there are consequences to choosing one way or the other. And if you get clear down here around 15 and you don't accuse them of cheating, then you just lost a bunch of money. So that's the way people are thinking about this. But here's the way scientists are thinking about it. They have a threshold. So scientists have a threshold at 5%. So if the outcome along this gradient here is 5% or less, in other words, if random flips on a fair coin could only produce the outcome 5% of the time or less, that is where the scientist goes into action and says something other than random chance is operating here. Now, it's very easy to figure this out. It's a binomial, what we call a binomial distribution. The binomial means it's heads or tails, or there's two sides to the coin. So right there is where the threshold is. It's about 41.6 or something like that. It's between 41 and 42 heads. It's where a scientist would say, any loss this far away from 50 or more is something that is so unlikely to occur by random chance that we have to conclude, we're compelled to conclude, something other than random chance is operating. So about 42 heads is 5%. So that's what we call, where the critical value, or what a scientist calls the critical value of the T statistic or whatever it is that we're using. Right?
So the 5% is plus or minus 5%?
No, it's 5% or less. In other words, if the likelihood of the outcome could occur 5% of the time or less, then only 5% of the time or less by random chance, we conclude we can't reasonably attribute the entire outcome to random chance alone. It would be an unreasonable explanation for the outcome. It would be unreasonable. So we conclude it's more reasonable to assume that the coin is unfair or that the process is unfair. Now, of course, the term unfair applies to this because it's a game of chance, and we're betting on one way or the other. But in science, what we're doing is we're betting against fairness. So see, what we want to do in science is we want the coin to be unfair. We want something other than random chance to be operating. In fact, what we want to be operating, what we want to demonstrate is that the treatment variable that we designed the experiment around, that's what caused it, not just random chance. So scientists would also conclude that the probability of something systematically favoring, this is the key word right here, systematically favoring heads over tails is greater than 95%. Now, one of the problems with contemporary science, because people have gotten so stuck on advocacy versus skepticism, is that they think this 95% can be attached to the treatment variable. So here's what most scientists think today, especially life scientists. They think that when they get a significant rejection of the null hypothesis at alpha, what we call alpha equals 0.05 or 5%, that they can be 95% confident that the treatment variable caused the outcome. And I'm here to tell you that is totally irrational. I'm here to confess that I had the same assumption for the first few decades of my life as a scientist, until I started getting deeper into this and realized this is not what is going on at all. Because all I can be 95% confident, hold on a minute here. All I can be 95% confident of is that random chance is not a good explanation for the outcome. And I can be 95% confident of that. But it is not publishable. So I can't, report on them. I mean, when I get a grant award from like NSF or something, I have to file a report at the end of the grant period. And I have to tell them what I found. Well, I can't file a report that says that there's a 95% chance that something other than random events were operating in the experiment, because it's inconclusive. So what is the probability that the coin is biased in favor of heads? So if I were to get down to, like, say 15, the likelihood of getting 15 heads in 100 tosses of a fair coin is like 0.000001. So that's very, very highly significant likelihood that this coin is not a fair coin or the process is biased somehow. And then the question is, so what is the probability that the coin is biased in favor of heads? Now, most people would say 95%. The answer to that question is unknown and unknowable. Unknown and unknowable. So then how in the world can we justify claiming that we've made a scientific discovery based on the results of a hypothesis test, when the best we can say is that random chance is probably not the only thing operating? So I hope this is really the clincher to your understanding what's going on with science. Now, like I tell my students, if you get to this point and you're thinking, I'm not quite sure I've got this, but I'll figure it out later, you're not going to figure it out later. So if you don't understand this and you really want to understand what's going on here, you got to say something. So this example right here wraps it up. This is this is the most rigorous possible, simplest, least complicated type of scientific analysis. These are the kinds of conclusions that we make. The most definitive conclusion that we can make when we run an experiment is that it was caused by something other than random chance. The only way we can go back and attribute this to the treatment variable is to go back to the experimental design, the design of the experiment, and think about all the different things that are operating and try to figure out if there's any other way of explaining it other than the research hypothesis. Anything other than, is there any way of explaining it other than the treatment variable having caused the outcome? Failing to find anything else that's a reasonable explanation, we can only reluctantly choose the treatment variable as the cause. So you see, the results of the experiment don't point to the treatment variable as the cause. The only thing that allows us to conclude that the treatment variable was the cause is that we can't figure out anything else that could have caused it. And that's it. That is the only thing. That is the only support we have for concluding that the treatment variable was the operational phenomenon in an experiment that caused the results to be non-random. And that was really bad news for me, because I was thinking that science was a way that we were figuring out what is actually going on. But all we're doing is finding things that is being able to figure out a consistent way of organizing information so that when we design systems, the way the systems work is consistent, so that most of the time the systems work the way we've designed them to. And
when you say most,
works,
when you say most of the time, are you saying 95% of the time?
No, I'm saying that the systems work really well most of the time, but you know, like the bumper sticker says, stuff happens and things go wrong. So in every system, things go wrong. You know, Murphy's Law.
Right.
If anything can go wrong, it will. And so now, see, when scientists first design systems, they're relatively crude, and they work, you know, pretty consistently, but they still keep failing. And as I look across the screen here, everybody is old enough to remember what the old cars were like. I remember I had a Volkswagen Beetle when I came here in '73. And that thing had an air-cooled engine. It was really a fabulous car, really simple. But I had to adjust the valves in that thing every 3,000 miles. I had to get in there with a feeler gauge and adjust the valves every 3,000 miles. And all the cars up until back, I guess, about the 80s or 90s, I had to change the spark plugs, had to adjust the points, and I mean, had to change the oil every 3,000 miles. And you remember, everybody where they parked their car on the driveway, there was always oil spots. You don't see oil spots anymore. So the systems are getting better and better and better. But the illusion is that we're getting closer and closer to figuring out what's going on. And we're not getting any closer than we were at the beginning. All we're doing is figuring out how to organize things so that most of the time they work the way we want them to. And it's actually an illusion that just because the systems are working much better, that we're actually getting closer to figuring out what's going on. So what do you think? All right, let's move on.
Well,
Yeah.
I'm trying to think, but what you see, I'm having trouble. The different types of hypothesis that you talked about.
Yeah.
Um,
Well, in this slide right here, Bob,
yeah.
the only two hypotheses in this slide are the null and the alternate hypothesis.
Okay.
They're statistical hypotheses.
Okay.
But notice this question right here. Let's see. What is the probability that a coin is biased in favor of heads? See, that's a phenomenological question.
Uh-huh.
Up to this point, all of these percentages here, they are statistical. And the only thing, like for instance, I can run what's called a t-test here.
Now, what is a t-test?
Oh, it's just a way of figuring out probabilities.
Okay.
It's a way of given a scenario, figuring out what the different outcomes are and what their likelihoods are.
Uh-huh.
And that's all the probabilities associated with science. That's all they are. Now, I don't know if y'all saw the news conference where Dr. Fauci was talking about that there was a really encouraging treatment that had about 1,000 subjects in it as the remdesivir.
Yeah.
And he talked about significant difference. And he said that the difference was significant on a large group. And he said that the effects, the magnitude of the effects were not where we want them to be, but they were able to shorten. So the average time, a reduction of time in the hospital was 3 or 4 days. So they were able to cut 3 or 4 days off a hospital stay. And then he said that difference was not where we want it to be, but it was significant. Okay, the significance came from this kind of figuring here. It came from statistical hypothesis testing. Now, what is the likelihood that remdesivir actually caused that difference? So if the p-value was 0.001, that means there's only a 1% chance that it could have been caused by a fluke, it just happened that way without remdesivir having caused the outcome. So what is the likelihood? This is a test. What is the likelihood that remdesivir was the cause of the reduced hospital stay? This is a question.
Okay, if I recall that press conference when he was talking about it, he was saying there were two groups, and one group was like at 35%, and the other group was at 25%. In other words,
yeah, that's right. Okay, so what is the probability that remdesivir caused that difference?
what is the probability? Wow, that's.
What is the probability that remdesivir, see, he said it was significant at 0.05. He said it was significant at alpha equals 0.05. Just like I've shown you in this little gambling game here.
Uh-huh.
You know, each one of these outcomes has a probability associated with it. So he was saying that it was down in here. It was less. It was, in other words, the difference was large enough that it would be unreasonable to say that it was just due to random chance. So that's what the p-value is. That's what significance means, is that it would be unreasonable to think random chance could have caused that outcome. But the question is, what is the probability that remdesivir was the treatment variable? What is the probability that they just demonstrated remdesivir as a cause? it's unknown and unknowable. And that's what he didn't say. And I would wager that he doesn't even know this, because most scientists don't. They've never looked into it this deeply. So the probability that remdesivir was the cause is unknown and unknowable. The way they attribute remdesivir as the cause is they go back and they look at the experimental design. How did they do? How did they treat the people? How was, is there any other way we can explain this other than remdesivir? Failing to come up with any other explanation, they're compelled to choose remdesivir as the cause. And that is what gets published. But that probability is unknown and unknowable and is subject to revision.
Okay. Why then, and why is there such a huge conflict with hydroxychloroquine?
Well, because if you're on the side of hydroxychloroquine, you're on Trump's side. I mean, that's the reality of it.
Trump doesn't have anything to do with it except that he said it. If Trump would have said remdesivir,
if Trump had not come out in favor of hydroxychloroquine, we would probably be using it a lot more than we are.
Okay, so if Trump came out and said he was for remdesivir, whatever it is,
yeah.
If Trump came out for it, would that mean that?
No, because that's not Trump's idea. I guess, I don't know. But
so you're saying science is political?
Yeah, it is very political.
Okay.
It certainly is. All right, let's move on here a little bit.
We're not talking about political science either, right?
No, we're not talking. Well, it actually is political science when you get right down to it, but people don't acknowledge it.
Well,
okay.
All right. Huh? I'm sorry. Well,
no,
I don't see how politics could possibly be a science.
Oh yeah, I know. Two possible outcomes when an experimental response is sufficient and consistent with prediction. Failure, and that means unable to reject the null as a sufficient sole explanation. Now, there's jargon in here, so let me remind you what this means. When an experiment fails, that means that either the results didn't go in the right direction or they didn't go far enough in the right direction to be useful. All right, so when that happens, we're unable to reject random chance as the sole cause. We're unable to reject random chance as the sole cause of the outcome. So that's what it means when the results are not significant. And that's what a failure is. Now, this word here is misleading because there's nothing that's really failed. It's just that we were hoping to get significant results and we were unable to get significant results. Now, that statement right there simply means we were unable to discount or dismiss random chance as the sole cause of the outcome. Unable to dismiss sampling variability as the sole cause of the outcome in the experiment. And if you can't dismiss sampling variability or random chance as the sole cause, then you're not justified in concluding that your treatment contributed to the outcome. So success, on the other hand, is when the null is rejected. And it would be ridiculous to conclude that this occurred entirely due to random chance. It is so unlikely that random chance could have caused it alone that we think something other than random chance is surely operating here. It's contributing to the outcome. Now, random chance is always operating. It's not an either or with random chance. Random chance is always operating, But what we're asking here, is it reasonable to conclude that something systematic has been applied across the experiment and contributed to the outcome? That's what we're hoping for in a successful scientific experiment. So that's what success means. Something systematically was applied across the experimental design to contribute to the results. But where is the research hypothesis in this? It's not. So these are probabilistic here. And we can assign definitive probabilities to these two. One of these is the null, and the other one's the alternate hypothesis. And those are statistical, and we get really definitive numbers on those. But they have nothing whatsoever to do with the real science and the experiment, because the science is in the research hypothesis. That's where we say variable A caused variable B.
So how does the research hypothesis work with the null hypothesis?
Well, they're not connected. They're not connected in any way. And that's what, guys, I have sat in group meetings with other scientists that are much more credentialed than I am. Some of them are famous scientists. And I have talked about this with them until I'm blue in the face. And they just get red in the face. And they have never challenged the logic. They just want me to shut up. They have never came down. I've invited them to come down and look at the logic. And they just won't do it. Now, some of them have, most of them don't. Some of them have. And they're honestly embarrassed when they actually look at the logic, because it's bulletproof. I mean, I think I told you about one where I was meeting with the people over at Grins or somewhere over to the broccoli restaurant. And they just got out and stormed out and left me there by myself. And I've had several confrontations like that. I've had people throw me out of their office. And never has anyone challenged the logic. So see, it's human nature to want to be in control. And science is such a trip, because you're finding all these ways of controlling the environment. But we want to be the priesthood of truth. So there's this aura in a department of science about we have the truth. And we are the ones that are able to figure out stuff. But the reality is, all we're able to figure out is how to do stuff so that we can predict the outcome and be right most of the time. But we still don't know what's going on behind the green curtain. So all the narratives we have telling stories about what's going on they're just made up. They're just made up. And we have scientific revolutions and we change the narrative, but we don't change the way we do stuff. We just change the stories we're telling. Okay, so successful experiments, on the other hand, support the alternate hypothesis. And the alternate hypothesis says that one or more phenomena contributed to the results. It doesn't say the treatment variable caused it. It just says something is going on. There's something systematically applied to the experiment that contributed to the outcome. The research hypothesis says what caused the alternate hypothesis to be accepted. However, it's not supported directly. So assigning cause, this is the key. Assigning cause is invariably subjective. It is not objective. It's not objective in the sense that, now it is objective in the sense that it's repeatable, and it's to some extent consistent. Other scientists can follow your methods, run the research in their lab, and come up with similar results. So it is objective that way, but it is not objective in the sense of objective truth. Assigning cause to the result of an experiment is subjective, and it's unavoidable. Not only that, but if somebody duplicates your experiment in several other labs, it doesn't add strength to your conclusion. It just adds strength to the alternate hypothesis, and that's all the alternate hypothesis says. Something's going on, but it doesn't say what. The only way we say what is subjective. So what is the scientific proof then? You've heard people say, if you get in a discussion with somebody and they're arguing back and forth, and somebody says, well, da-da-da-da-da-da, and that is a scientific fact, or that's been scientifically proven. Well, that's the end of the argument, right? I mean, that's just, okay, let's talk about something else now. But that's an illusion. So a scientific proof is a sufficient response followed by rejection of random chance as the sole cause. In other words, it went the way we expected it to, and it went that way strong enough that we can reject random chance as the sole cause. So this directly supports the alternate, and the alternate says something's going on, and we have a specified probability. Something systematic likely happened. The research hypothesis is assigned as a cause only because we can't think of anything else to assign the cause to. Bob.
Okay, my question is, if you, a scientist who has been doing this for 50 years, cannot, with ironclad evidence, sway a modern scientist, how on earth could we as lay people, why would we even want to get into a conversation with them regarding this?
Well, the last part of your question is the question to address. I don't know why anybody would want to. The reason I'm doing this is to dispel the illusion that science can reveal truth. Therefore, we need to get science to line up with our faith, or our faith to line up with science. So that's my only purpose here. This is our artificial dichotomy to insist that science, so the argument goes, well, science is dealing with truth and the Bible deals with truth, so they're going to have to come to agreement somehow. That's an artificial construct, and it is based on an illusion. And that illusion has a historical foundation that I think started with Sputnik. So, okay. And that's just my world. I'm sure other people have other explanations. So, but your question, if I can't convince anybody, I sure wouldn't advise any of y'all trying to convince anybody. But so the reason I'm telling you about other scientists being so resistant to this is because you need to understand that there is human pride involved in science, and it is overpowering. So we have these conventions, and there's a power structure in these scientific conventions, and the people that are in power don't want to give it up, and they're reluctant to agree with anybody that that says what their power is based on should be rejected. So they fight it. And
so your earlier premise that older scientific research was very strongly influenced by skepticism, whereas today's science is strongly influenced by advocacy.
That's right.
That is more of a clear understanding that could be taken away from what you're teaching, which somebody who is skeptical, I mean, Christians can be skeptical of their faith. I mean, this is what Bible study is all about. This is why we study Scripture.
Yeah.
Not to prove something we already believe, but to learn something that is bedrock solid. Because, for example, it says in Isaiah 26:3, it says, God will keep in perfect peace whoever keeps their mind on him, because they trust in him. And then it says, trust in the Lord forever, for the Lord himself is the rock eternal. Well, that you could be very skeptical of that statement, but if you put it to the test, God does turn out to be a very stable rock. But people don't believe that without having had some kind of experience
Yeah.
where that is proven to be true for them.
Yeah.
Somebody who trusted God and it appeared that God wasn't a solid rock, they're going to have a hard time following the Lord.
Yeah. And of course, there's a lot of people that do that and reject even the premise of there being any God, because they insisted that God meet them on their terms.
Right. That's
And
exactly right. But when you are, when a person is coming out of darkness into light, they don't have that much light upon which they can examine truth. So I would say skepticism is okay as long as a person is honest.
yeah.
I think, and it's not just intellectual honesty. I also believe it's any kind of honesty. You and I have talked in the past about intellectual honesty.
Yeah.
But in reality, honesty is honesty. It's facing the truth, no matter where it takes us.
Yeah.
So I think, or not I think, from what you have told me, the issue for me would be between advocacy science versus skepticism. And advocacy science cannot be true science.
Yeah. Well, it's let's just say, instead of using the word true here, let's just say it's not good practice. Skepticism is best practice, and advocacy is dangerous, because you are likely to go in a direction that you want to instead of being led by the data. So anytime we impose an expectation on interpretation, then we're in dangerous territory. And not only that, but our conclusions are much more likely to be overturned in a fairly short order.
Okay,
I see
so,
we're approaching 3 o'clock here, Bob. So,
yeah. Okay, I just want to say this. Exegesis or skepticism to science is what exegesis is to theology.
yeah,
Whereas advocacy is to science what eisegesis would
right.
be to
That's good. Yeah,
theology.
yeah.
Okay. Well, thank you a lot, David. I must confess, much of what you said today was over my head, but I'm going to keep coming back. This is
Well, we're about to
very
get
rich.
into, I know I keep saying this, but you know, it just takes time, and we're going to be getting into sort of wrapping up the scientific method part of this and getting into scripture, and sort of we'll be able to stand back and take a look at the whole thing and answer that most important question, which is, so what? So what? All right.
Brent, did you have any questions?
Nope.
Well, thank you for being here today.
I had to mute it though, because, just in case I cough or something.
Okay, no problem. John, did you have any questions? Okay. John doesn't
I
have
will
any
unmute.
questions. Okay.
I have no questions because I find Dr. Huffman, because I come from a pure science background, I mean, a mathematical background. I only had one class in stat, and so I find it all very interesting. I enjoy it.
Good.
Oftentimes I don't understand it because I'm not a scientist,
Yeah.
but I still enjoy that, Dr. Huffman. I really do enjoy it.
Well, good. I'm glad to hear that. I appreciate that, John.
But I am, like I said, it's been a long time, but from a mathematical standpoint, I find it very interesting to me, all your background in science.
Yeah. So you know about the binomial.
Oh, yes, sir.
Yeah.
And
So
so I found, but there's so little of what I understand about all this. I understand the mathematical conscript, but I don't understand the scientific.
yeah.
So that is very interesting to me.
But you know, we have just briefly, we have in biology, we have a lot of scenarios that are binomial, like
Yes.
mature versus immature, like and male versus female. So if we go out and randomly trap a bunch of critters and bring them in, and then we sex them, the default expectation is approximately 50-50 males and females. So what if we find that it's off quite a bit?
Yeah.
What is the likelihood that random chance caused that? We go straight to the binomial to answer that question.
And that portion I truly understand, because it's very difficult when you do that. But I appreciate it.
Yes, sir.
Thank you.
David, could you turn off the share screen?
Oh, yeah. Yeah, remind me to do that, Bob. I mean, I keep forgetting about that.
Okay. Well, let's close. Father, thank you for this time we've had together. We look to you to continue to guide us and lead us. Thank you for Dr. Huffman and what he's sharing with us. Thank you for the little bit that sinks in and penetrates our mind. In Jesus' name, amen.
Amen. Thank you, brothers.
Good to
See
see
you
y'all.
next week, God willing.
3 o'clock?
Yeah, 3 o'clock next week.
Okay, back on regular time. Bye.
Yes, sir. Okay.